Okay, so let us have here example number 1. Determine whether e to the x, e to the 2x, e to the 3x are linearly independent or not. So again, we can find the linear independence of the functions using or by evaluating the Wronskian determinant W. So W, you have to take on the first row the functions e to the x, e to the 2x, and e to the 3x. And then on the next row would be its first derivative. So e to the x, 2, e to the 2x, 3, e to the 3x. And for the last row is its second derivative. So you have again e to the x, 4, e to the 2x, and 9, e to the 3x. So in order for us to find the determinant, I am not sure up to this time what method you know already in evaluating the determinant. So to illustrate, let me show you using the diagonal or the basket method. Using the diagonal or the basket method, the procedure is that you have to copy the first two columns. So copying the first two columns, e to the x on the next column, and then e to the 2x, 2e to the 2x, and 4e to the 2x. Then, it is called a diagonal or basket method because you actually draw diagonal lines going down and going up, and then you take the product of those terms in the diagonal line. So the first one, you have e to the x times e to the 2x times 9e to the 3x, which gives us the product of 18e to the 6x. And then the next term, e to the 2x times 3e to the 3x times e to the x, that is 3e to the 6x. Then the next diagonal, e to the 3x times e to the x times 4e to the 2x gives us 4e to the 6x. Then, now we take the product of diagonal lines going up and to be multiplied by negative 1. So e to the x times 2e to the 2x times e to the 3x times the negative 1, so minus 2e to the 6x. The next diagonal line, 4e to the 2x times 3e to the 3x times e to the x times the negative 1 is minus 12e to the 6x. And the last one, 9e to the 3x times e to the x times e to the 2x times the negative 1, so minus 9e to the 6x. And simplifying, that is 18 plus 3 plus 4 minus 2 minus 12 minus 9. That is equal to 2e to the 6x. Now, since the Wronskian determinant obtained, which is 2e to the 6x, is not equal to 0, therefore, the given functions of e to the x, e to the 2x, and e to the 3x are linearly independent. Okay, so now let us have example number 2. Determine whether e to the x, cosine x, sine x are linearly independent or not. Again, by evaluating the Wronskian determinant. So the elements on the first row of our determinant are the given functions e to the x, cosine x, and sine x. Then for the next row, you take the first derivative, e to the x, negative sine x, and cosine x. Then the second derivative, e to the x, negative cosine x, and negative sine x. Then again, copying the first two columns, e to the x on the first column, then cosine x, negative sine x, and negative cosine x on the next column. Then taking the product of the elements on the diagonal, going down are positive and going up are to be multiplied by negative 1. So the first one is e to the x sine squared x. The next diagonal is e to the x cosine squared x. Then you have negative e to the x sine x cosine x. Then the diagonal lines going up, you have negative e to the x sine squared x times the negative, so that is positive e to the x sine squared x. Then you have negative e to the x cosine squared x times negative, so positive e to the x cosine squared x. Then you have negative times negative, so positive e to the x sine x cosine x. And then simplifying, that is now equal to, that is 0. And then you have here factoring out e to the x. So you have, factoring out 2 e to the x. You now have 2 e to the x times sine squared x plus cosine squared x. And we know this is a trigonometric identity which is equal to 1. Therefore, our Wronskian determinant is 2 e to the x. And again, since the Wronskian determinant is not equal to 0, what can you say about now the given functions? The functions e to the x, cosine x, and sine x are linearly independent. Okay, so let us have now the differential operator. So what is this differential operator? This is actually the derivative with respect to x. So if you have dy, it means derivative of y with respect to x. If you have d squared y, that is the second derivative of y with respect to x. And if you have d to the ky, that is the k derivative of y with respect to x. The expression a is equal to ao d to the k plus a1 d to the, that is d to the n, d to the n minus 1 plus up to ao d to the n minus 1 plus a sub n is called a differential operator of order n. It may be defined so that operation which, when applied on a function y, yields to ay is equal to ao, the n derivative of y with respect to x, plus a1, the n minus 1 derivative of y with respect to x, plus up to a sub n minus 1 derivative of y with respect to x, plus a sub n times y. So the coefficients of the operator may be constants or functions of the independent variables. Equality of differential operators. Two differential equations A and B are equal if, when the same result is obtained from performing the operation on the same function. If A equals B, then AY is equal to BY. It means that A is applied to Y and B is applied to Y. Notes that you have here some notes. Take note that differential operators are linear operators. That is, if A is any differential operator, C1 and C2 are constants, and F1 and F2 are any functions of each possessing the required number of derivatives, then A times C1 F1 plus C2 F2 is equal to C1 times A of F1 plus C2 A of F2. The fundamental laws of operation are actually applied in differential operators. So just to review, the following are applicable. So the commutative law of addition, A plus B is equal to B plus A. Associative law of addition, quantity A plus B plus C is equal to A plus quantity B plus C. Associative law of multiplication, quantity AB times C is A quantity BC. The distributive law of multiplication with respect to addition, A quantity B plus C is AB plus AC. And if A and B are operator with constant coefficient, then they also satisfy the commutative law of multiplication that AB is equal to BA. So always remember these fundamental laws of operation that can be applied also to differential operator. Sorry for the error in spelling of operation. Okay, so let us have here example number 1. Let A equals D plus 2 and B equals 3D minus 1. Find ABY and BAY and also determine whether AB is equal to BA. Take note that the differential operators have constant coefficients. Coefficient of D is 1 and coefficient of for your B is 3. You have 3D. So our ABY, you have to introduce B to Y. So D plus 2 and then our BY is 3DY minus Y. Okay? So evaluating now, you have the derivative of 3dy, so that is equal to 3, the second derivative of y, and then minus the derivative of y. Then 2 times 3 derivative of y is 6 derivative of y minus 2y. Simplifying, you have 3d squared y plus 5dy minus 2y. That is your ABY. And therefore, to find your AB, it is simply 3d squared plus 5d minus 2. Now, we go to evaluating your BAY. So, you have to apply A to Y. So, your B is 3d minus 1. And now your AY is dy plus 2y. You now have 3 times the derivative of y is 3 the second derivative of y plus 6 derivative of y minus dy minus 2y. Simplifying, you have 3d squared y plus 5dy plus 2y. That is your BAY, and therefore finding BA is equal to 3d squared plus 5d minus 2. And comparing your AB and BA, they are found to be equal. Take note again that it is true if you have constant coefficients. AB is equal to BA. Example number 2. Let A be equal to XD and B is equal to 3D minus 1 and determine ABY and BAY and let us see if AB is equal to BA. So again, the difference in example 1 and 2 is that here, I make the coefficient to be a variable x. So let us have your ABY first. So ABY. So B is introduced to Y. So you have XD, and your BY now is 3DY minus Y. Okay? So we have here X, then you have the derivative of 3 times the first derivative, so that is 3, the second derivative of Y, minus the derivative of Y. And then, so you now have here your 3x d squared y minus d or x dy. And therefore, your AB will now be equal to 3x d squared minus xd. But for BAY, your B is 3D minus 1, and your A is XD, so that would be XDY. Again, as I told you, you should not do this as simple multiplication. If you do the simple multiplication, this is your result. That would be 3 times the derivative of x dy. If you do multiplication, that is 3x d squared y minus x dy. And your BA will be equal to 3x d squared minus xd. And then you will be saying that they are equal. But again, this process should not be done if you have a variable coefficient. No? So what you are going to do is to take note that it is, okay, that it is actually derivative and not simple multiplication. So for BAY, your B again is 3D minus 1, and your AY is XDY. So for the first term, you have 3, the derivative of x dy, and then minus x dy. So focusing on this, it means the derivative of the product. So this will now be equal to 3 times what is the derivative of the product x dy. So the first term x, the second derivative of y, plus dy times the first derivative of x with respect to x, so you have dy minus x dy. So you now have here 3x, the second derivative of y, plus 3 dy minus x dy. That is your BAY. And now finding BA, that is 3x d squared plus 3d minus xd. So you notice that there is a difference now of the term 3D. Again, it is because you take this as the derivative of the product. The derivative of the product of x dy is x, the second derivative of y, plus dy times the derivative of x with respect to x. Okay? So this should be now your BA, and therefore, you will be concluding that AB is not equal to BA. So generally, if you have variable coefficient, AB, or the product of the two differential operators are not equal. Special case siguro if you arrive at, even though you have variable coefficients, is that still you can have your result to be equal. Okay? Then we go to the next, which are the sum properties of differential operators. We have here some properties of differential operators that you can use later on our next module. So the first property is the d to the n e to the mx is equal to m to the n e to the mx. So let us show, if you have the derivative of e to the mx, that would be equal to what? M e to the mx. What about the second derivative of e to the mx? That is m times m, so m squared e to the mx. What about the third derivative of e to the mx? So the third derivative would be m times m squared, so that is m cubed e to the mx, and so on. So if you have the n derivative of e to the mx, that is equal to m to the n e to the mx. Okay, so later you need not to differentiate it n times, but you just can have it as this number one property as m to the n e to the mx. Number two property actually is if you have a polynomial function of the differential operator d, f of d, to be equal to ao d to the n plus a1 d to the n minus 1 plus up to a sub n minus 1d plus a sub n. If we apply e to the mx to this, what will happen? So f of d, applying e to the mx, is equal to ao d to the n e to the mx plus a1 d to the n minus 1, sorry, that is d to the n minus 1 e to the mx plus up to a sub n minus 1 d e to the mx plus a sub n e to the mx. Then applying our first property that d to the n e to the mx is m to the n e to the mx. So this would be ao m to the n e to the mx plus a1, that is m to the n minus 1 e to the mx plus up to a sub n minus 1 m e to the mx plus a sub n e to the mx. To the mx, okay? And then, if we take e to the mx in each term on the right side, so you have e to the mx, that would be now ao m to the n plus a1 m to the n minus 1 plus up to a sub n minus 1 m plus a sub n. And this terms now is actually a polynomial function of m. So you have here a polynomial function of d applied to e to the mx is equal to e to the mx, a polynomial function of m. So this will be actually used in the forming of the so-called auxiliary equation, why a differential operator can be formed in the so-called auxiliary equation, which physically, as you see, is just changing the differential operator d to m. But this is actually the property of the differential operator, why we can have that. And if m is the root of f of m, then what happens if m is the root of f of m? Then therefore, this is equal to 0. Then you have f of d, e to the mx is equal to 0. Again, if m is a root of f of m. Okay? So the next property, property number 3, is the so-called exponential shift. Why exponential shift? Because you're actually to shift the differential operator either going to the right or to the left of your e to the ax. Or it can be your e to the ax will be shifted from right to left of the differential operator. In the first one, you have d minus a e to the axy. It should be equal to e to the ax dy. Let us show this one. So you have d minus a e to the axy. So that is equal to d of e to the axy minus ay. So you have the derivative of the product. So e to the that is e to the ax dy plus sorry for this one. This is minus a e to the axy. So for this, the derivative of the product e to the ax dy plus y times the derivative of e to the ax with respect to x. What is the derivative? So that is a e to the ax. And then minus this term, minus a e to the axy. So this is a e to the axy minus a e to the axy. This is 0. Therefore, this is e to the ax dy, which is this one. We just showed how this left side is equal to this one. Now, let us try if n is 2. On the second line, you have d minus a squared e to the ax. What would be its equivalent? So, by expanding, you can actually have d squared minus 2ad plus a squared e to the axy. So you have the second derivative of e to the axy minus 2a, the derivative of e to the axy plus a squared e to the axy. Okay, so we will just simplify and we should end up with e to the ax d squared y. So you have to take the up to the second derivative of this. So let us have the first derivative first. So that is e to the ax dy, that is the derivative of e to the ax dy plus a e to the axy. Then you have here minus 2a d of e to the axy plus a squared e to the axy. So you have here derivative again of this term. So you have e to the ax, the second derivative of y, plus dy times a e to the ax plus a squared e sorry, that is a e to the ax dy plus y times a squared e to the ax. Okay, then minus 2a and its derivative here. Or actually, we can take it here. Because this term is the derivative of a e to the xy in this one. Anyway, 2a times e to the ax dy, then you have minus 2ay a squared e to the ax plus a squared e to the ax dy. Okay, let us see. Let us see the common. You have here dy ae to the ax and dy ae to the ax. And then you have here negative 2a e to the ax dy. So this, and this are 0. Then you have y a squared e to the ax, y a squared e to the ax, and negative 2 y a squared e to the ax. So these are also 0. And therefore, you now have e to the ax d squared y. That is your d minus a squared e to the axy, which is actually this. So in general, if you have d minus a to the n e to the axy, you should end up with e to the ax d to the ny. So you need not to show this long process. That is the purpose of introducing the properties of differential operator. You just take note that if you have this d minus a to the n of e to the axy, then it should be equal to e to the ax d to the n y. So take note, why is it exponential shift? If you notice, we have shifted this e to the ax On the left side, it is after D, or the differential operator D, but we shifted it to the left of D on the right side. So when you shift it to the left, actually, we remove this minus A by actually adding A. So similarly, it follows that if you are to shift e to the ax to the right, you will be subtracting A here. Okay? So take note again, exponential shift, shifting e to the ax to the left of the differential operator, you have to add A to remove or to eliminate actually this minus A. But if you are to shift the exponential e to the ax to the right of the differential operator, then you have to put minus A in our differential operator. Okay? So again, you need not to show the long procedure of evaluating the derivatives, but you may just use the property. So remember this property number 3 called exponential shift. Okay, then we have here the next slide, the fourth property of the differential operator. So d minus a to the n, e to the ax, x to the k. So this is also a very important property for you to lessen actually the length of or the time that you consume for the solution. This is actually applying yung ating exponential shift. So let us have this d minus a to the n, e to the ax, x to the k. So if we apply exponential shift, we want to shift e to the ax to the left. So again, we should be adding a. So plus a, therefore, this is simply equal to e to the ax, d to the n of x to the k. The fourth property actually is referring to this part of finding d to the n or x to the k. Depending on the values of n and k. The first case is if n is equal to k, what would be the derivative, for example, the third derivative of x cubed? So the derivative of x cubed, the first derivative, that is equal to 3x squared. And then the second derivative of x cubed would be equal to 6x. And the third derivative of x cubed would be equal to 6. How do you find this 6? 6 actually is equal to 3 times 2 times 1, which is simply equal to n factorial. So if you are asked what is the d to the fifth of x to the fifth, so you need not to take 5x to the fourth, then you have 5 times 4x cubed, etc. And you will be ending up with your answer as 5 factorial or 120. The case is what if n is greater than k? Excuse me. Okay, so the second case is what if n is greater than k? Say, what is the fifth derivative of x cubed? Okay, so again, similar to this, we found out that the third derivative is 6. So let me just continue here. So what is then the fourth derivative of x cubed? That is now 0. And the fifth derivative of x cubed is 0. Okay, therefore, in general, if n is greater than k, then the derivative of d to the n x to the k, if n is greater than k, is equal to 0. And the third case is what if n is less than k? Say, for example, what is the third derivative of x to the fifth. So the first derivative of x to the fifth is 5x to the fourth. The second derivative of x to the fifth is 20x cubed. And the third derivative of x to the fifth is 60x squared. So how are we going to generalize this? To generalize, if n is less than k, so the n derivative of x to the k would be equal to, what is 60? 60 is 5 times 4 times 3. So it is not factorial. So 5 is this, k. So k times k minus 1 up to what? What is the last factors? So 5 times 4 times 3. What is 3? 3 actually is 5 minus 3 plus 1. Okay, so up to k minus n plus 1. So you will be taking the consecutive product of k times k minus 1 up to k minus n plus 1. And then multiplied by x to the k minus n. Okay? So that would be the general. So that you need not to do the long process of taking the derivative or the nth derivative of x to the k. Okay, so that is the end of module 4 discussion, in which we discuss again the general linear differential equation solution for homogeneous and non-homogeneous, and then followed by the discussion of the differential operator, and then you have the properties of the differential operator and also the linear independence of solution. So I hope that with this video presentation and the annotated PowerPoint or presentation, you will be able to learn this module number 4. Thank you very much.